Good morning, everybody. This morning, I'm going to talk about a rather old subject, nutation. And it happened that during my scientific work, I never had a chance, any opportunity to consider nutation, which is first was introduced in the mass spectroscopy, but as early as in early 70s, Professor Sam Weissman suggested and demonstrated that nutation experiments might be of real importance, real interest in EPR spectroscopy as well. He realized the following experiment. He just used the common steady-state EPR stuff in the system where no paramagnetic particles were existing. But then by short light pulse, excited triplet organic molecules were produced in rather highly polarized, hyperpolarized, we would say today. Now I see my presentation. So Sam Weissman suggested and realized this nutation experiment with excited triplet molecules. And in discussing this, he and his colleagues pointed out that this method might be of really wide applications in EPR. But then, from my point of view, this method did not get wide distribution for several reasons. Sorry, why it is jumping? Since I wanted, could we come back to the previous? Okay. And then it did not develop very much for reasons which I will tell about them later more. But recently, my colleagues in Zavoysky Institute, Andrei Sukhanov and Valery Tarasov, demonstrated on our seminar very interesting results. They were studying these terbium centers in some monocrystal. And they found that they were studying nutation. Nutation was observed using primary spin echo signal, and they found that the same ions, which can be stabilized in different microscopic positions, they give different periods for the nutation. So you see, example, the third curve, this down curve, the period is definitely different. And it happened that this ratio is square root from 2, ratio of these periods, and which shows that this down curve relates to the paramagnetic centers with total spin 1, while the upper curve corresponds to the paramagnetic center with spin half. That means that down curve relates to the dimer of two ions. So this, of course, is rather convincing. And then it gave me impact to think more about, and I decided to go to study more carefully nutation. And now I would like to share some observations, theoretical observations, which I did when studying literature. Next, please, next. How I can, okay. So in the literature, I found that there is a definite justified belief that nutation method can be used successfully to measure the magnitude of electron spins. And of course, magnitude of electron spins is very important parameter and not easy to measure by other methods. For example, for transition complexes of transition elements, like in previous example from Sukhanov and Mendeleev and Tarasov. Also, for example, for electronically excited molecules, for example, there are some investigations, studying the excited Fullerian, triplet Fullerian molecules when stable radicals are attached to Fullerian. And there are examples when several radicals can be attached. So we have some multi-electron association, which can be in states with different total spins, and to find them, to identify this method might be of real interest. Next, please. Next. Why this method is not very much developed in EPR spectroscopy until now? The reason is that usually we have EPR spectra very much broadened, inhomogeneous. There are many reasons: hyperfine interaction, zero field splitting, and inhomogeneity of magnetic field, many reasons, which do not permit to produce non-selective excitation of spins in this nutation experiment. But at the same time, it is known, and it happens, that the excitation pattern is of absolutely great importance for the nutation pattern. What happens with the nutation? For example, in nuclear, in NMR field, it might be rather easy to realize non-selective excitation when the interaction with the radio frequency field is much larger than the inhomogeneous PR case. We have normally opposite situation. Since theoretically it becomes rather difficult to calculate, to simulate time dependence of spin system under the action of high power microwave field. For that reason, theory is developed not very much, and of course, this does not allow to widely use notation in experiment. Okay, further. Next one. Next slide. Thanks. So I already announced that I'm going to present some specific points. Maybe it might happen that everybody except me understands this, but since it was, I did some small but nice theoretical observations, I decided to share it with you, and this will, at least now I understand very well how this notation frequency, what we are observing as a notation frequency, as a notation, can depend on a microwave power. So, and it is clear for me now that in principle, with all these possibilities of computers, even without quantum computers today, we are able to extract all magnetic resonance parameters, all parameters we can find from steady state EPR spectra. even including the also spin lattice relaxation, which of course we can measure also, we can find also from the steady state experiments, solving some stationary equations. But everything can be done with notation experiments, since we can do all calculations. Theory is developed well enough to be able to feed successfully experimental data with theoretically simulated ones. Why I think it might be interesting? You know, when pulse EPR spectroscopy was developed, it happened that many questions can be successfully resolved using pulse EPR spectrometry, and this is fine. But majority of spectroscopies in depth has the typical steady state EPR spectrum. So for them, it might be like a good message to know that with steady state EPR spectrometer, with some much less expensive upgrading of the instruments, it can be converted to the time resolved experiments. And with that, one can detect nutation signals as well. So I think that notation in principle deserves more attention than it has today. Пожалуйста, дальше. Next one. So just I remind you, in notation, basically when Tori considered, it was the of the system, magnetization of the system to the sudden instantaneous sudden switching on of the microwave power. But Tori considered that the spin dynamics is determined totally just by the constant magnetic field B0 and by the microwave field B1, nothing else. Usually, spin dynamics, which can include also not only what is some phones are not that is bad. Here should be, instead of this quadrats, there should be omega 0, omega z, and omega 1 Rabi frequency Sx. Sorry, since our computers have different fonts. Okay. So to see what kind of information can be found from the notation experiment, let us consider a very simple example. And in advance, I will tell you that this simple example concerns the case of non-selective excitation of spins. All spins will be excited on the same pattern. This is similar to NMR situation. Then it happens that in a rotating frame, for example, frequency Z, where omega is the frequency of microwave field, omega 1 is the Rabi frequency of microwave field. Then we say, let us suppose that system was in equilibrium state just before the switching on of microwave power. then density matrix at some moment will be determined by this well-known parameter, this equation. So from this equation, we see that any time dependence of nutation of this transient signal will be determined by this Hamiltonian. And that means that all as oscillations of the signal, we see the coherences in the spin system produced in this stage. So that means that what we are observing as a time dependence, it means that we observe different coherences which appears under the action of microwave field. And if we will work in the beginning, usually we work in the calculation basis of the eigenstate as better to jump into another calculation basis. It's better to consider this time development of coherences in the eigenfunction basis of Hamiltonian in rotating frame. Then it immediately appears that the nutation frequency will give us all possible differences of energy levels for the Hamiltonian in rotating frame. In principle, we might say that in principle, we can see all possible EPR transitions, for example, in linear response EPR spectrum, in linear response for the second microwave or maybe radio frequency for the second alternating magnetic field. But the important thing is that not all possible coherences we will see all possible we will see, since, for example, it will which one in principle we can see will be determined by the initial density matrix. So SZ, of course, will not have even in this new basis, it is not necessary that SZ will have all non-diagonal elements, non-zero elements. And then the second thing is that we have to observe these coherences. We observe them, for example, in typical EPR spectra, we measure the Y component of magnetization. So in principle, signal which we observe might give us all possible frequencies of all transitions between sorry, it is my I put my my time is over already. It is typical for me. Next, please. Next, please. It happens, this problem can be easily solved, and it happens that if microwave field is in resonance with Zeeman frequency, we see nice notation with the frequency equal to ω1 Rabi frequency. And this frequency does not depend on the value of spin. So with that, we see that under this condition, we see as a notation frequency ω1, and it does not contain information about the spin value, which is basically one of our main goals to be able. And here I demonstrate how this for the same model, how the notation will change if there is a distribution of Gaussian distribution of Zeeman frequencies. And if we pop on the center of this Gaussian distribution, we will see the very sharp. So there are oscillations, but the frequency of oscillations, they are so the period is increasing slowly. Finally, asymptotically, we will come to the period determined by omega 1. So if there is a distribution of the frequencies, we cannot determine exactly nutation frequency by observing the most sensitive part of the curve. There will be some shift of that frequency, which can be calculated theoretically. So for that reason, we will need some fitting. Theoretically, so we should do that. Otherwise, we can see, for example, there is a part which we do not observe in experiment, and we will say, oh, okay, we see there are oscillations, but this period is not equal to the omega 1. Omega 1 will be just asymptotic value. Please, so we need real fitting. Next one, to do the Fourier spectrum. Next. Okay, now, okay. The interesting thing is that in this absence of this omega 1 is just terrible. Since you see, when in this particular case, when we pump with the resonance frequency microwave field, the spin dynamics will be determined as with this operator, exponential operator minus E omega 1 SXT. Nothing else. When this frequency is omega 0 and equal to omega, we will have this term. The interesting thing is that if there will be spin, arbitrary spin, then Sx is the matrix which has different non-diagonal elements neighbor to the main diagonal. But this transition matrix elements are different, and we know how they look like. But then it happens, despite the fact that matrix elements of transition between neighbor states in the SZ basis, despite that fact, it happens that the eigenvalues of this operator give equidistant spectrum separated by the value omega 1, independent. So in principle, there should be notations with the frequencies omega 1, 2 omega 1, for example, starting from spin 1, 3 omega 1 starting from the, in principle, for spin 3 over 2, we might expect 3 notation frequencies. Whether we will observe them or not depends on the initial state of the, if we will prepare some polarized non-equilibrium, for example, in case of equilibrium initial state, it happens that independent on the value of spin S, we are able to observe, to detect only one frequency, omega 1, manifests itself. Other ones do not manifest themselves. But it depends on the type of initial state. Please, next.
Excuse me.
Next.
Time is end, please.
Okay, further. So for that, we should observe, for example, quadruple moment, which is created during optically polarization of electron spins. Further. Next slide. Next slide. Please, next slide. Алло, вы меня слышите, нет?
Саша, следующий слайд.
Да вот, а где следующий слайд? Я его не вижу. Вот теперь увидел. So now you see, to introduce selective excitation of different transitions, let us complicate the Hamiltonian. For spins one or larger, let us introduce some quadruple term, d as z squared. In that case, it happens that what will happen that if we have, if we will, even in that case, we have the interactions with microwave field omega 1 S6. So this non-selective excitation. If we will introduce, and then also if frequency of microwave field omega equals to the Zeeman frequency plus this quadruple interaction term, then Hamiltonian in rotating frame will have this on diagonal two equal levels, and we have the third energy levels which is separated. Depending on the d value, it might be separated a little or it might be separated a lot. And important thing is that what is the ratio between this interaction, is this splitting, and b omega 1. This Hamiltonian is written for spin 1. Now we see definitely that larger than omega 1, we can in zero approximation to drop out transition matrix elements between 0 level and T2 levels. In the first approximation of the perturbation theory, I can put here 0 and 0. Then we come to the situation which is presented below this one. So we have the, I do not see the whole screen. Okay, there will be, this will be 0, 0, 0. And then it happens that we have two degenerate levels which are coupled by the transition matrix element. Then we find the collective modes. In this particular case, they will be symmetric with plus, so-called plus and minus states with minus. And these collective modes will be split by omega 1 multiplied by square root 2. So it will be just the difference of the difference between two the split energy levels will be square root from 2 multiplied by omega 1. In case when if here d will be 0 as well, then it will happen that the energy levels, collective energy levels, will be omega 1, 0, and minus omega 1 for spin 1. But when we split it, one of the levels very much split it, then it happens for this, in this particular case, we will get the difference between these energy levels, which will be a square root from 2 multiplied by omega 1. So this explains what happens in the limit situations. But in principle, in theory, we can have, please next, we can have the any values of d, and I did the numerical calculations. Please next one. Okay, further, since I am out of time. Next. Okay, we see the scene curve corresponds to the case when d equal 0. Then it happens that now period is determined, this nutation frequency equals to omega 1. We increase this quadruple interaction d term There are the figures. Then you see this period becomes shorter. It becomes shorter. The maximum shifts to the left. Then even further, when d equals 1 Gauss, and here omega 1 is also 1 Gauss, that time we are close to, so from 0 to 0. This is the period. So and then it happens that now we are close to the frequency. Periods became shorter, frequency increased. It is close to the square root from 2 to omega 1. So you see, here we see how changing the quadruple interaction, we shift nutation frequency from omega 1 to square root from 2 to omega 1. And here are the calculations for larger values of the 2 Gauss, 10 Gauss, 30 Gauss. So, and you see, all this period is around square root from 2 multiplied by omega 1, close to this curve, the sick curve. Okay, maybe I will jump to the conclusion. Since I'm sorry, I'm very much out of time. Just my message is the following. Since in principle, we can calculate carefully the reaction of the system to the sudden instantaneous switching on of the microwave field, in principle, by some upgrade of steady-state EPR spectrometer, converting it to time-resolved EPR without using very short pulses with very high B1 fields, we can, in principle, we can get a lot of information. Of course, the fitting procedure might be rather complicated, but I think that so then we will need to make Fourier transformation of the notation, and then we have to find the, and also during the fitting procedure we can find the notation frequencies as a function of microwave power, and the same we can find from the Fourier transformation of this notation signal. And I think we come to typical situation when we have the complex spectra. We have to make simulation, we have to fit, but this is, I think, nice additional method. And in this method is more direct to determine value of spin from experiment in compared to the, for example, steady state experiment. On that case, again, we can, in principle, we can have this spin value as a fitting parameter as well. But from omega 1 from B1 square dependence of the notation frequencies, it is definitely more direct way to judge, to make some judgment about the value of spin. So thank you very much. Since I have no time to continue, but I hope that I succeeded to give you some impression that in principle it is we are able to understand, to describe how depending on the excitation pattern, how notation frequency shifts from expected frequency omega 1, which is expected from Bloch equations, for example, and how to reveal to manifest the differences in transitions of matrix element between different states for the spins more than half. And the interesting thing is that you see, at first I thought that maybe notation frequencies or the set of notation frequencies gives us the EPR spectra in rotating frame. In fact, it is not the same. From in EPR spectra and from the Fourier transformation of the notation signal, we will get the same frequencies. Maybe some of them we will not see, since they might be forbidden for the EPR observable. But they will differ not only by the set of frequencies, but also by the intensity, amplitudes, how different harmonics enter into the EPR in the rotating frame and into the notation signal observed. Thank you very much.
Thank you for the interesting lecture. Unfortunately, due to technical problem, we don't have time.
I'm very unhappy with that.
Unfortunately, we don't have questions, but during virtual coffee break, I think we can talk with.
Okay, then
I have about your reports. Now
to feel myself that. Okay, coffee break.
Now is coffee break. Unfortunately, this coffee break will be shorter, only 10 minutes. Thank you all participation for.
So excuse me, please. Let me. I hope that you see. I will be very happy if anybody will send me his question. So please. Please pass to everybody who will be interested my email. You have it. I will be very happy to contact and to answer and to discuss. In particular, since now I spend a lot of time alone at home, I will be very happy to discuss anything, any questions. Okay. And by the way, I do not see Bernhard Blumich. He was in the list. Okay. Okay, so you're very welcome. Thank you very much. That вы не забросили меня там помидорами. Хорошо. До свидания. До свидания.
The coffee break for 10 minutes.
Я тоже пошел кофе пить.
Leaders, we will begin at 10:15 in Moscow time.
5 minutes only.
Only 5 minutes. О, ну я вас очень прошу.
Когда мы все-таки начнем? 12:10 или 12:15?
Ну да, то знаете...
10:15. 11:12.
Мне личные просьбы. Дайте людям попить.
Moscow time, certainly.
А то они меня возненавидят. Скажут, из-за него без кофе остались.
Хорошо, 10 минут.
Спасибо.
May I try the screen demonstration?
Yes, of course.
Спасибо. Так.
Хорошо. Пошел кофе пить. Да. Вот все кончил. Ну, как всегда, я не уложился во время.
Я просто хотел, ну вы...
Я уже кончил. Сейчас там кофе. Ну, все. Ну, у меня, как всегда, я не уложился во время.
Уважаемый, видно мой экран? Кто-нибудь?
Да, видно, отлично все.
Все хорошо, тогда надеюсь, что справлюсь повторно. Спасибо.
Please.
Uwe, do you have a question?
Well, I have a question to. I have several questions to Kev, of course, but I think you better drink your coffee.
Okay.
Hello, Kev. Can you hear me?
Включите, пожалуйста, звук, профессор Салихов.
Okay. Okay, sorry.
Yes, Kev, can you hear me?
Now, yes, I hear all with you, but it happened that I was switched it off. Now I am switched it on.
Yes, Kev. I have several questions. I enjoyed very much your lecture,
Please,
actually.
please.
Yes, on your second slide, you showed some signals. Your lecture was mainly theoretical. And how have these signals been registered? They are quite fast.
They were okay. They. Of course, it was not the typical Tori experiment. You know what happened is do the following experiment. You apply this microwave field during some time, which is changing with, of course, from one experiment to another one. Then you switch off this microwave field, and then you give another pulse and detect echo signal. So you detect MZ component and MZ component, not MY component, but MZ component, since in primary echo, we observe signal proportional to the MZ in the initial state.
I see. But actually, these signals are very fast. They are in the range of nanoseconds. So they are difficult to record. On the scale of your slide, there have been the
nanosecond. You mean echo signals?
Yes. And I think that's a general.
This is, you see, if one. You see, if omega 1 is, for example, if P1 is 1 Gauss, then the frequency will be 10 to 7, and that means that period will be about 100 nanoseconds.
I see. Yes.
100 nanoseconds.
And of course, the problem is that with very short pulses, actually, and low power, you can excite only a small part of the spectrum. So what do you actually observe? I think you do. Maybe I'm not right, but I believe that probably what you are looking at. Yes.
In this experiment, as I expect, they observe this nutation signal with rather low B1 field, maybe half Gauss, since for a long time the system might be heated a lot, so they escape that. And then they do not, for example, Weissman suggested to make this, to integrate the signal at any time in some short interval. So how it is done in normal time resolved EPR spectroscopy. There is a stationary time resolve. When you accumulate the signal in some short interval, and you just shift this interval of integration. In this case, in case of Sukhanov, they use not this technique. They were doing the following thing. Ions are in equilibrium. Suddenly, they switch on microwave field for rather long time, for example, half Gauss. And then they switch off it. And after that, they get some non-equilibrium state of magnetization, which is measured by typical Han two-pulse echo signal. So you see, it is like in the experiment inversion recovery, we use echo signal to follow that magnetization.
I see. But anyway, isn't it like that you excite only a very small part of the broad EPR spectrum, and what you observe actually afterwards probably is some kind of spin diffusion of the excited spins through the whole line.
You are totally right. If we would excite the whole spectrum, we would not see this increase of nutation frequency.
Mhm.
Which arises exactly for the reason, and this is the typical situation. Normally, in EPR range, it will be very rarely possible to excite the whole spectrum. Practically, very rarely it will be. Typical situation will be we will excite. So this excitation pattern determines dramatically what we will observe.
Well, thank you, Kev. It's more clear to me now. Thank you.
It creates real. In many cases, it is safe to think that excitation might be non-selective, and in MR we can say, aha, this pulse will be 90 degrees, this will be 180. In EPR, it happens that this does not work. We always have some rotated on the 90 degree, other one on 70, and the third one on 20 degree, and other ones.
Yes, probably that is also
should be taken into.
Yes, probably that is also the reason that it is less used in EPR than in NMR.
Yeah,
because
sure.
in MRR you can excite the spectrum completely. You never can do it in EPR.
Definitely, no, this is definitely the reason why it is less used. Definitely, but just I was thinking, you see, then one is not able with his EPR spectrometer. Usually, this is solved using the pulse technique. Since in pulse technique we can use rather high B1 field, order of magnitude higher magnetic field, and which makes the situation much better. And then, but if somebody has not this pulse EPR spectrum, he might nevertheless to solve many problems if he will use, for example, Weissman was able to make nice words with nutation at the time when no pulse technique was existing.
Thank you, Kev.
Okay. And my suggestion, and I think that in principle, it also, I will continue since I met this, and I was wondering how this for spin 1, how omega 1 is transferred to omega 1 multiplied by square root from 2. This I wanted to, it was strange for me. Now
dear colleagues, excuse me, but it's high time to continue.
Okay, it was nice to see you, and maybe we will meet each other more. Okay, I go to drink coffee.
I hope very much, and I'm very glad to see you at the screen in such a good shape, Kev.